Okay, so welcome again to another video lecture series for Physics 2. So today's discussion would be on magnetism. Okay, so this is actually the second half of the discussion on electricity and magnetism from the title of our coverage, electromagnetism. This means that the first half is on electricity and the second half would be on magnetism. Okay, so with this lecture, we will start with concepts of magnetism and its many application and how is magnetism related to electricity. Okay, so for today's video lecture series, we will be discussing the nature of magnetism. We will be comparing and contrasting electric force versus magnetic force. We will be describing the concept of the field for both of the two forces described here, electric force and magnetic force. History of magnets, the interaction of magnets, unmagnetized objects, and magnetic poles versus electric charges, and the Earth as the magnetic field, and magnetism, the relationship of magnetism and current. Okay, so let's start with the first topic discussion, which is the nature of magnetism. Okay, so magnetism is the interaction of moving electric charge. Try to compare it with our discussion on electrostatics, wherein our discussion is limited only to the interaction of charges that are at a certain distance with respect to each other, and they are assumed that they are not moving with respect to each other. So therefore, that is why we have the name electrostatics. This means that these charges or electric charges are at rest with respect to each other. Now, for this topic wherein we have another type of interaction, but this time the type of interaction happens between electric charges that are moving. Okay, so this type of interaction basically adds to the type of interaction that happens when charges are at rest with respect to each other. So on top of the interaction that happens to the charges when they are at rest, we have an additional um, interaction by virtue of the movement of these charges with respect to each other. And we call this type of interaction as magnetism. Okay, so magnetism acts only on moving charges. So this means if we have or if we set up charges that are at rest with respect to each other, they will not exhibit any magnetic interaction. Okay, so the collection of moving charges is what we call electric current, as we already know at this point. Okay, so let's try to compare and contrast electric force versus magnetic force. Okay, so as we know, electric force, this is the type of electrical interaction or interaction that acts between charges whether they are moving or not. Of course, we have discussed this in our early presentation of Physics 2, and this is quantified using Coulomb's law. Okay, so if you remember Coulomb's law states that the force of interaction between the two charges is directly proportional to the product of the charges and at the same time inversely proportional to the square of the distance in between them. So at the moment that they are at a given certain distance, whether they are moving with respect to each other or not, the interaction is being quantified using Coulomb's law. And the type of interaction that happens in between the two charges is electrical in nature. Whereas if the two charges being considered here has a relative motion with respect to each other, they in addition to the electric force quantified using Coulomb's law, we have an additional force we call the magnetic force uh, that is exhibited by virtue of the movement of the charges. Okay, so this additional interaction is exhibited only when the two charges do have relative motion with respect to each other. Otherwise, if they are not moving with respect to each other, then there would be no magnetic interaction that would be exhibited. Okay, so just like what we have discussed uh, in the discussion on electric forces and electric fields, the electric field concept or the field concept is the idea that uh, we have established that in order for a charge to send its interaction and to have its presence felt by other charges present within a given region, this presence is established in the form of establishing a field or particularly an electric field if that field is established by an electric charge. By virtue of the electric field, one charge can send its presence and therefore its force of interaction to other charges within the vicinity of its presence. Okay, so by the same idea, we could also a moving charge could also send its presence and its interaction to other moving charges within a given vicinity by establishing the same field concept, but this time it is called a magnetic field in addition to its electric field. Okay, so um, the electric field arises in two stages. The charge produces an electric field in the space around it. The second stage is that the charge within the presence of the electric field responds to this field. In the same manner, if a charge establishes a magnetic field within a given region, a moving charge or a collection of moving charges produces a magnetic field. Any charge that are in relative motion to the source of the magnetic field shall experience a magnetic interaction in the form of a magnetic force in reaction or in response to the established magnetic field within the given region. Okay, so this means that the ultimate source of the what we call a magnetic interaction is virtually the establishment of the magnetic field by virtue of the presence of the source charge that is moving. Okay, so the ultimate source of any magnetic interaction is the movement of a charge or moving electric charges. Now, just like in electricity, there are actually two types of interaction that happens between charges that are at rest. So this is repulsion or attraction. So the same goes with magnetic interaction. There is also attraction and repulsion, but this time, this happens between sources of magnetic fields. So between, for example, two bar magnets or two charged particles that are moving with respect to each other. So let's focus first on two bar magnets. So two bar magnets attract when opposite poles, for example, north and south or south and north, are next to each other. So this means in the same manner that you have two opposite charges, if you have two opposite charges, the tendency of these two charges, they attract each other. So the same goes with magnets. If you have two opposite poles of a magnet, the tendency for these poles is for them to attract. While if you have two bar magnets that are put next to each other but pointing with the same poles, so for example north to north and south to south, the tendency of these two magnets is for them to repel each other. So just like in our electrical interaction, if you have two positive charges that then set up within a given vicinity or within a given region, the tendency is for them to repel. The same goes with two negative charges. Now, question: Which pole of a bar magnet will attract an unmagnetized object that contains iron, such as a nail? So the answer is either pole, meaning a negative pole or a north pole could attract an unmagnetized iron object, such as a nail. The same goes with a north pole. So either pole of a bar magnet can attract any unmagnetized object. So for example, north can attract metal objects such as a nail. The same goes with south pole. Okay, so let's try to compare magnetic poles with electric charges. Okay, so unlike a bar magnet, an electric charge could exist in separate or distinct parcels, such as a as a positive charge and a negative charge. So you can have a distinct electron that carries a negative charge. Also, you can have a distinct positive charge or a proton, distinct or separate from a negative charge. Now, let us compare that idea with a bar magnet. So, can we have a separate north pole for a magnet? Or can we also have a separate south pole for a magnet, just like what we have a separate positive charge and a separate negative charge? So what happens when you break a bar magnet into two pieces? So if you're going to break a bar magnet into two pieces, what happens to each piece is that each piece would have its own north pole and its own south pole. So this means if you break a magnet into two pieces, the two pieces of magnets would have its own north pole and its own south pole, meaning the resulting pieces of the magnets would still be on its own a magnet. So therefore, you cannot actually isolate a north pole on itself or nor a south pole by itself. So if you actually continue this process of breaking the two magnets further, the resulting piece every time would be a magnet that has its own north pole and its own south pole. In contrast to electric charges, magnetic poles always come in pairs and cannot be isolated. Okay, so consider this process of continuing breaking up the magnet into smaller and smaller pieces. That this means that if you eventually end up with the smallest possible piece of the magnet, of course, the smallest possible piece for a magnet, which is the smallest possible piece for any object, is the atom of that object. This means if you break up a magnet into smaller and smaller pieces, and that every piece is a magnet in itself, this means that the atom is actually a magnet in itself. A magnet in itself which has its own north pole and its own south pole. Okay, let's consider another situation, the Earth as a magnet. Now, we know that the Earth is a magnet because simply because of the basic idea that a compass needle, by the way, is a magnet in itself. The compass needle reacts to the magnetic field of the Earth. By virtue of this idea, we know that the Earth itself is a giant magnet. If you are familiar with the idea of a magnet, that the compass needle of a compass always points towards the north direction, or the north geographic pole. But virtually anywhere in the globe, even you're on the northern hemisphere of the Earth or in the southern hemisphere of the Earth, the compass needle always points towards the north. So regardless of your place in the globe, the compass needle always points towards the north. Therefore, if you replace a magnet at any different location around the globe, the compass needle would always react to the magnetic field of the Earth, always aligning itself towards the direction that points towards the north geographic pole. So this indicates that the Earth itself is a giant magnet. Okay, so since the compass needle has its own north pole and its own south pole. Of course, by virtue of the discussion earlier, that the type of interaction that happens between the poles of a magnet is that they would attract, north and south would attract, south and north would attract, opposite poles would attract, and similar poles would repel. This means that if the compass needle is always pointing towards the north pointing, that means that the actual pole of the north pole is actually south magnetic by virtue of the convention of the interaction that happens between magnets. So a south pole would actually attract a north pole. So this means if the compass needle that points towards the north geographic pole is north pole, therefore the north geographic pole of the Earth is actually the south magnetic pole of the Earth. And in the opposite direction, the south geographic pole of the Earth is actually the north magnetic pole. Okay? Now, another curious thing about magnetism is that magnetism or a compass needle actually reacts to the presence of any current carrying conductor. So this phenomena was actually observed by William Ørsted. So what happens is that he accidentally discovered this phenomena. So what happens is that he has this setup of an experiment, and he tried to turn on the circuitry in the setup so that so that he knows that there is a current that is flowing through the current carrying conductor. So it just so happens that that there is a compass that is present within the there is a compass needle that is within the region of the presence of the wire. So what happens when he turned on the current is that the compass needle actually reacts to the uh, presence of the current carrying conductor. He noticed that when he turns off the current flowing through the wire, that the compass needle returns to its original position, that is pointing towards the north geographic pole of the Earth. So this indicates, Ørsted concludes that if if a current carrying conductor influences the magnetism of a compass needle, this means that a current carrying conductor could be a source of magnetism in itself. Okay, so this discovery actually links the idea of electricity with the ideas of magnetism, paving the way to the more general study of electromagnetism. So by this time, upon this discovery, electricity is no longer treated as a separate subject, separate from magnetism, but is considered as two sides of a coin. Okay, so just like what we see here in this diagram, when the wire carries no current, the compass needle virtually points towards the north geographic pole of the Earth. While if there is current flowing through the current carrying conductor, the compass needle would orient itself towards the direction of the established magnetic field due to the magnetism of the current carrying conductor. Also, Ørsted noticed that when he reversed the direction of the current, what happens to the compass needle is that the compass needle would orient itself in the reverse direction as before. Okay, so this ends our introduction on basic ideas on magnetism and the connection of magnetism to electricity.